Yeah. Okay, so we start last class this week 6. We are in insulation, talking about insulation. We looked at some of the common R factor or R value for some material. And we talked about water and insulation. We said water is not a good thing to have around insulation for the following reasons. It will fill up the air cavity, which we depend on to insulate. Air is a good insulator. Not bad at all. Air is a good insulator. We talked about how air can insulate and how hot air warms your body. So if you bundle up like this, the air around your body is like warm and you're keeping around your body. That's why when you have wind and the cold wind, the wind is not going to warm air from your body. That's why when it's really cold and there's no wind, it feels better than when it's less cold with wind. That's why they tell you there's a wind chill factor. That's why they tell you 50 but feels like 35. It has to do with the humidity and also the wind. So again, if it's hot and if it's cold, the wind does make a difference. Okay? We see the water, we don't want water in the insulation because it fills the airspace. Water and ice. If we have water in the house and condensation, eventually it's going to freeze and cause some ice dams in your attic. Corrosion is an issue for water in your insulation. So water is kind of something we don't want inside our structure. And what do we use to keep the water away from the house? What do?
We wrap it.
We can wrap with something called craft paper. You have wax paper. You have different kind of sheet and rubber to keep the water away from the house structure. You want to keep the water from the outside, not have it migrate inside the house. And not even just concerned with the inside of the house, also the cavities inside the wall. So between the outside and your wall, you also want to keep the water away. Also, it's a big source of bacterial growth. And who said also, somebody said wood rot last class. It can cause your wood to rot. If wood rots, it's gonna fall apart. And a lot of people have a lot of moisture in their basement or their attic space, and the wood eventually deteriorate over the years, and it will cause the house to collapse. So that is something you have to pay attention to. If anybody gets mold in their walls, what do they usually do? They put huge air dryers and they dry every bit of moisture inside your wall, and that will eventually deprive the bacteria from growing, and it will die. If you look at vacuum sealed food that lasts forever, they put, of course, some preservative, but also they try to eliminate the air from coming in and out and moisture. A lot of food also, dried food, they put those little silicone packets to absorb any kind of extra moisture. So you don't want to have moisture, and also you don't want to have air to keep things preserved. Which makes you think, a lot of oxygen will help oxygenation, oxidizing of material, but also moisture will promote growth of bacteria. So oxygen. What else helps slows down bacteria?
Slows it down?
Yeah. So it feeds in oxygen and water.
Cold.
Cold. That's why when you put food in the fridge, it will last for a week. The freezer, 6 months. The deep freezer, maybe around a year. No, a year, I think it's maximum. You cannot slow it that much. So again, that's why even frozen food has expiration date on it, depending on the kind of food. So bacteria and the decomposition of meats and food goes faster, and a bit slower when you close it down. Okay, I want to talk about something called thermal mass and thermal inertia. What do you think when I say thermal mass?
The amount of thermal, the mass, like the
Quantity of thermal energy. So thermal mass is a way for us to hold big or large amount of energy. So who was saying something about cement last class when we were talking about cement?
Yeah.
So you're talking about cement and concrete and how concrete, actually you were saying something. It stores a lot of energy. So that's called thermal mass. So some material have big and large thermal mass because they can store energy. Some materials don't. Can you give me example of material you think that will hold their heat?
Iron.
Metals are not good because they are conductors.
I thought iron holds on to heat for a long time.
No, it conducts quickly. It cools fast.
Dark wall.
If you use a steel cup for coffee, ceramic cup, which one will cool faster? Steel. And also steel is a good conductor, so it will lose heat quickly. So usually ceramics, that's why they have clay pots. Concrete holds a lot of heat. Stone holds decent amount of heat.
Sand.
Sand holds kind of heat, that's silicon. Wax, oils, all these materials can hold heat for a longer time. Water is a good mean to store heat. That's why even though it's 0 degree outside, you can look at some lakes and some ponds, it's still not frozen. It takes a while for it to lose all its heat. So it takes time. It has good thermal mass. It's storing heat from the summertime. There are some buildings, actually now in many places in Europe and Finland, where they actually design a whole building with a big tank in the bottom that gets heat up in the summer using solar rays, and they use that heat to heat the house in the winter. You can store a lot of heat in the water. If you notice also, if you have a cup of water, it takes a while for it to cool off. It doesn't cool off right away. So water is a good substance to store heat. So energy absorption and storage, it varies from, this is a factor, 1 to 2.6, you don't have to remember that. And it increases the R value. So if you have material that have more thermal mass and thermal inertia, which means like it can store heat, it will be helpful for you to preserve heat. Inside insulation have 1.5 mass factor because it holds its heat. Your jacket holds heat, right? You take off the jacket for a few minutes, you put it back, it still has some heat. It doesn't cool off quickly. So you want something that actually holds on to heat, doesn't cool off quickly. Depends on the material and also depends on the configuration. Hot climate benefits a lot from higher mass factors than colder climate cities. So in hot climates you can use material with mass inertia. There was a time when there were a lot of initiatives and projects into designing houses that have enough and good thermal mass so you have more passive heating and cooling. Meaning if I use the right amount of cement and clay, the house might not heat as fast, I might cool off it at night faster. I remember there were houses in Africa and the Middle East where they make the basement made out of clay and the walls are very thick and they are tapered. So it takes a long time for this house to heat, and from the morning until like 4 p.m. it's not hot because it takes a lot of time to penetrate all this wall with heat. So by 4 o'clock the sun is already cooled off. Whatever heat is stored will be released during the night, slowly and very fast, and it will continue heating and cooling just using mass heat and mass inertia. So thermal mass is how much heat you store, and thermal inertia is how fast you dispense of that heat. So usually we use a lot of ceramics and non-conductors. Would you think plastic have good thermal mass? No, it does not hold heat. It does not conduct heat. So you want material with good thermal mass. Mostly ceramics, some kind of liquids, some kind of gels. What about if you play sports? Probably use an ice pack. Those ice packs you keep in the freezer. They have a gel in it, right, which lasts for a long time. And there are a lot of research in those things that you can break and mix, and they have a lot of thermal mass, thermal inertia that can dispense over a long time. So this is some kind of an example of what is thermal mass and thermal inertia. Again, going back to insulation, what is insulation? Is made of minerals, matter that traps air. Could be anything. That's how we came up with the newspaper thing, which is the cellulose. Cellulose is a fancy word for newspapers. And plastics also, they can trap heat depending on how they weave them. A lot of if you look at your jacket insulation, there's little fibers inside, plastic or nylon or polyester, which is also kind of plastic. The way they are woven will trap heat. Glass fiber, or fiberglass, also holds a lot of heat and traps air between its cavities. And cellulose. which again, egg crate, old boxes, paper products are cellulose. So these are the basis of insulation. Wall insulation, they call bats. This is something that we want to install in the house before you put in the drywall and in the outside. And they are cut precisely to the size of the cavity inside. And sometimes they have foil sheet. What is foil sheet is good for? What do we use foil sheet?
Radiations.
Radiation. It counteracts radiation, it reflects. And we also use craft paper or wax paper for the moisture. And most of this stuff is treated to be fire retardant. Fire retardant now is being regulated more than before because of a lot of chemical issues. But again, they are supposed to be non-combustible. What does non-combustible mean? You cannot burn it?
Won't
I mean,
ignite.
will not.
Won't light up on fire.
Yeah?
It won't ignite.
It's
It's
fire
normal
rate
operating.
Yeah. So everything burns and melts, but it would not ignite.
Okay.
Like a paper, you can heat it, some of it will ignite. This thing will not ignite. Your car, huh?
Like diesel and gas.
Yeah,
Diesel combusts, but it doesn't
yeah, true.
ignite.
So there's no ignition, there's no, how can I say, chain reaction. It will burn, but it will stay, it will not ignite. For example, a lot of carpets are not combustible. They are combustible. They call it non-combustible. It means like if you drop, for example, a cigarette on it, it will burn a hole, but it will not ignite completely. It will not cause a chain reaction and burn the entire thing. Carpets, mostly car material, are not combustible. It does not that doesn't burn. It can burn it, but it's not going to combust and start flame. No ignition. What else? So they are non-combustible. Density and weight. That is something very, very important to talk about, especially if you do insulation, which will bring a lot of awareness to how insulation is done. So what is density and what is weight?
Density,
Somebody have that?
mass over volume, and weight is force times acceleration. Sorry, mass times acceleration, take that back.
I love my triangles. So mass times volume. Right? No, mass is here.
Yeah.
So density is mass over volume. Another triangle.
So the same law basically as ohms?
Yeah.
Depends on that.
It's a relationship between three items. I like the triangle because it helps me remember. And what is weight is
Mass times acceleration.
mass times gravity acceleration. So mass equals density over volume. And why do we need to know that?
So you can find out.
Your R values,
It's not good. It's good weight. Weight is enough.
Weight, that's, weight is different from mass.
Hmm?
so it's not mass, but weight.
It should be weight. or
Weight, it should be weight.
mass.
Huh?
Yeah, it's gotta be mass. Mass is not weight.
But if you get if you get the mass,
Yeah.
you multiply by the gravity and you get the weight.
Yeah, so.
And weight equal mass. If we say mass times gravity, it's gonna just confuse people.
9.81.
Let's just keep it simple. Times acceleration of gravity.
9.81.
Gravity. Let's not do that. Just remember, weight equal density times volume. And what is the unit of weight? Pounds density pound per foot cube. And this is foot cube. So why do we need that? Because going back to the insulation part, when you're stuffing a lot of stuff in small cavity, what are you doing? You're increasing the density, and that actually makes a difference when it comes to insulation. So volume again, depth, width, and height over this number to give you foot. Again, let's be mindful of the units. So if we have depth, now we're talking about a cavity in a wall, for example. Depth in inches, inches, and inches. If you wanted to convert inches to feet, you're gonna divide by 1728, 1728, which equals to what? 12 times 12 times 12. Because this is what happens. We have two inconsistent units. You get go measure with inches, but you want the volume in foot cube
Oh,
to make it consistent. Nobody can measure with foot. So you'll go, look at a cavity, and you're gonna go and do 6 inches times 28, etc. This then you convert that into feet. Make things a little bit easier. And the conversion is again, because it's 12, it's really hard to convert that. So you take the measurement in inches and you convert the answer into feet. Make sense? So you get the volume, you multiply that by the density or the required density, because when you buy insulation, it is sold by the density. So you know how many pounds you need to pump of insulation inside that cavity or inside that attic. So again, what are we trying to do here? We have a cavity in the wall, we're trying to fill it, we find the volume, and we multiply that by the density that is recommended for that insulation. So I know how many pounds should I put in there. So if, for example, if I put 2 pounds, I'm required to put 4 pounds. I put 2 pounds and it's full. What are you gonna do? You're gonna try to let it settle, then compress it a little bit, then you put some more. And that's why when you have those cellulose insulation in the attic, they spread it, then they wait until it settles. Don't try to compress it, they let it settle a little bit. And they have a machine that will push it down a little bit after you come back, and then you can put the right amount per weight. Basically, this calculation. Otherwise, you're not going to get the right amount of insulation. Make sense? Then you're gonna put it there, they fluff it. You might get chipped in the amount of insulation you put. After a couple of weeks, it will settle down, and you find you're not getting the R value that you actually designed for. So it's good for you to have the right amount of insulation. And that's why we need to calculate the volume and find the weight, so you can know that you bought a bag of 10 pounds and this 10 pounds has to go in that cavity. Make sense? So you know how much you're gonna put in that wall. And again, because most of loose insulation, it gets fluffed out and get pumped using kind of like a fan or a motor or a agitator, air agitator to pump it into the cavity. Example. Wall has 3.5 inches deep. This is the depth of the wall. Reasonable. 14.5 cavity and 93 inches in height. So it's a small cavity between the two studs. Here's an example. And cellulose has a density of 3.6 pounds per cubic feet. How much do I need? How many pounds of insulation we need for that cavity in the wall? And again, the good thing about water insulation is you already have a dry wall, so you don't have to take it out. You can just cut a hole and just pump some insulation in it to retrofit it. So I want to know how much I'm going to pump, 2 pounds or 3 pounds or how much. Because when you pump it, it's going to be loose, it's going to fill out, so you can wait for it to settle. Might try to compress it a little bit and put some more. So if I want to do this example, what is the volume here?
3.5 times 14.5.
Volume equal 3.5 times
14.5
14.5
times 93.
times 93 cube. 19.75 inches cube. Divide that by that magical number. 4719.75.
2.73 feet. Cube.
2. What is the number? 17. 28.
What'd you get? Oh, yeah, that number.
Wait, where'd you get that 17.8 from, or is that the?
That's the conversion factor between the inches. This is 12 times 12 times.
Oh, okay.
Convert from inches to feet. So I got 2.73 for volume. How much? So weight equal volume times density. 2.73 times density, which is giving us 3.6. So you will weigh the amount of insulation you need to pump in and put it inside the cavity. Questions? How to calculate water volume?
We use it in pounds. I mean, I'm still stuck on this. We use in pounds because we don't have a unit in our system for mass. Well, we do,
Yeah.
slugs, but we don't
Yeah,
use that.
yeah.
So you do the 2.73 times the 3.6.
Yep.
And mass is used for engineering.
Do you know?
How did you get the 9.5? I'm sorry.
Yeah?
How'd you get the 9.5?
I rounded up closer, and then you go by 9.8, the clock's conversion.
Yeah, because it's 9.828.
Yeah, around 9.5. Or you can go to 10.
This is how you find out how much insulation you
Yeah.
need with the wall.
Wait, yeah, wait, yeah.
So the insulation to this varies by how thick the wall is, the size of the wall.
Yeah,
doesn't have
and
to-
yeah, we're talking about weight.
And the weight.
Yeah, if this is for, this is for one insulation. Question?
Oh no, I was gonna say, like, you know how there's slugs, and there is such a thing as a slugette. It's like Dr. Bob came up with that term.
I'm done with engineering. Let's keep things simple. Okay? Questions? Okay. So let's do one room on the project. I'm gonna do it, and you're gonna follow through in the
Steps.
with the steps and do it. And let's start from the beginning. I'll get the paperwork.